Okay, welcome back to Virtual Science 2020. Today, we're going to start talking about some of the special behaviors of gases. Because gases, the particles are completely free to move about, they do some things that solids and liquids can't do. There's a couple of special things that we want to look at with regard to gases. Now, before we talk about gases in general, we need to talk about the idea of pressure and what pressure is. Pressure is defined as the amount of force exerted per unit of area. So your weight is a force. It's the measure of the force of gravity. So if you think about, like if you stand on your tippy toes, you have the same force, which is your weight, exerted over a tiny area. So you feel a lot of pressure on those toes. If you have the same force, which is your weight, exerted over a large area, like if you lie flat on the floor, then you don't feel so much pressure because that same force has been spread over a large area. Force is measured in pressure is measured in a unit called pascals. It's after the man who originally did a lot of the work with pressure. Now, air pressure inside of a container, like inside of a ball or tires or a balloon, is the result of the particles, which we've been talking about the particles. They're moving, and with a gas, they're completely separate. So the particles are bumping into the side of the container, and they're pushing out on it. So like with a tire, the air in the tire, the particles are moving fast enough that they're bumping into the sides of the tire, and they're pushing outward, and that's what gives the tire its air pressure on the inside. So the more particles you put in there, the more of them there are to push out on the sides of the tire, and so we would say the tire has more air pressure. Now, I wanted to just take a look at the difference between air pressure in a container and air pressure in the atmosphere. So we said in a container, air pressure is the result of the particles pushing out on the sides of the container. But the air pressure that we talk about when we say air pressure at sea level or air pressure in the room is a little bit different. And you can think of air pressure, it's very similar to water pressure. So when you're in a swimming pool and you're at the bottom and you feel that water pressure pushing on your ears and you feel it pushing, it pushes everywhere around you. It's pushing on the top of your head, it's pushing on the side of your face, it's pushing on your hands, it's pushing underneath your hands, it's pushing in all directions the same. And the reason why you feel it down at the bottom of the pool, particularly on your ears, pushing inward, is because it's the weight of all the water above you in the pool. So the deeper you go into the pool, the more water there is above you, so the more weight of that water is pushing, and it pushes in all directions. It's pushing in on your ears, and so you feel it. Well, in a lot of ways, the atmosphere is like a great big swimming pool, but instead of the pool being filled with water, it's filled with air. And we're at the bottom of the pool. So the air pressure that we feel is just like this water pressure down at the bottom of the pool. It was the weight of all that water above us. What we feel down here at the bottom of the atmosphere is the weight of all the air above us. And just like the water at the bottom of the pool, it's pushing in from the sides and in from the top and underneath our hands. So we don't feel it just pushing down on us. It's pushing in all directions. Now our bodies are acclimated to that pressure. So we really, most of the time, aren't aware of it because it's just constantly pushing on us and we're adapted to it, so we don't feel it. But sometimes you can feel the change in pressure when you go up higher. So if you go up a mountain, like if you're driving from here and you go up Afton Mountain, as you go up the mountain, sometimes your ears will pop. The reason why that is because you're getting higher up, like I drew this guy in this airplane here. Okay, as you get higher up, there's less weight of the air above you pushing down on you, just like if you start to come up from the bottom of the pool and you're only 2 feet deep. Well, you don't feel that much water pressure on you anymore because there's not that much weight of water above you. So as you go higher in the atmosphere, There's less weight of air above you, so you feel less air pressure and your ears push out and they pop. Sometimes you can feel those changes. Now, one of the reasons why these old kind of airplanes had, it was called an open cockpit, so the pilot was just sitting there, and as he flew, he was just breathing in the air around him. As airplanes became better and better, and they could fly higher and higher, there wasn't enough air pressure in the higher parts of the atmosphere for a person to just be sitting there. So they had to close these in, and they had to start putting glass over them, and eventually they had to start pressurizing the cabin. So like a jet has a pressurized cabin. That's because we're not adapted to being this high up where there's this little air pressure on us. So our bodies would be pushing out. Like when a doctor checks your blood pressure, what he's doing is checking how much your body is pushing out, and then of course the air pressure is pushing back. If you get too high up, your body is just pushing out, and there's not enough air pressure, there's not enough weight of this air pushing on you to push back. So these airplanes, the cabin is called pressurized. So it's just like being inside of a balloon. And when you see in a movie, like if something happens, it's like popping a balloon. The air blows outward. So what happens is it's just like being inside of a balloon. When there's a hole in it, everything goes out the hole. So you see people get blown out of the airplane at this high pressure because the cabins are pressurized. Okay, and that's different than the pressure of the air inside of a container, like we said, inside of a tire or inside of a basketball. Now, one of the things that happens at these higher altitudes is it does affect the boiling point of water. So I wanted to share this this box of cake mix, and I wanted you to see here where it says high altitude, over 3,500 feet. Heat the oven to the same temperature, okay, but it tells you to cook the food longer. So it says if you have two 8-inch pans like this one up here, and it, you know, where it's lower where we are, it says to cook this cake 26 minutes, and down here at the higher altitude it says cook it 28 minutes. The two 9-inch pans, it says cook it 26 minutes, and here it says cook it 23 minutes. And the reason why that is because there's less air pressure at that higher altitude, so water actually boils at a lower temperature. So you have the liquid water, and remember the particles are trying to get separated and shoot off by themselves when they turn to a liquid. Well, the less air pressure there is pushing down on the water to keep it in a liquid, the easier it is for the particles to shoot out. So when you're cooking at these higher altitudes, the water boils at a lower temperature, so the cake, it's not at high enough temperature to cook the cake, so you have to cook it for a longer time. That's another example of how air pressure affects our everyday lives. Okay. Now, the first scientist we're going to deal with, his name was Boyle. And there's three variables in the gas laws. There's the space, the volume, the pressure on the gas, and then the temperature. And Boyle worked at a constant temperature. So it says over here, at a constant temperature, when the pressure increases, the volume will decrease, and then the opposite is true. As the pressure decreases, the volume increases. So where it says at constant temperature, one of the things that's hard to remember is who did what. Remember, Boyle didn't boil, so he kept the temperature constant. Now what he said is at a constant temperature, as the volume increases, the pressure will decrease. So I put 5 gas particles in this little box. And if we increase the volume and allow them to expand into a bigger space, the pressure is going to go down. Now think about the kinetic theory, and we said the pressure comes from the particles running into the sides of the container. Well, when they're squeezed into a small space, they're going to hit the sides of the container more often. When you let them go the same number of gas particles in a much larger container, okay, they're going to hit the side less often, so the pressure will go down. The other case, the exact opposite is true. If we decrease the volume, so we take these same 5 gas particles now, and we've got them in this great big space, and they're bumping into the sides of the container. They're not pushing on it that often because they're in a big space. If we squeeze them down into a small space, like when we compress them, these 5 gas particles are going to hit the sides of the container more often, so the pressure is going to increase. A lot of times I just remember when we talk about Boyles Law, and so when the temperature is constant, whatever one variable does, the other one goes in exactly the opposite direction. Okay, the word for that is inverse, but here we say the volume goes up, so we went from a small volume to a big volume, the pressure goes down. So in the big volume there's less pressure. And then the other case is the exact opposite. We went from a big volume to a small volume, so the volume is going down, the pressure will go up. So if the temperature is constant, whatever you read about in the problem, the one goes up, the other one goes down. They go in exactly the opposite directions. Okay. And then there's a short video clip of a demonstration that I want to show you on Boyles Law. This little clip is going to show us Boyles Law. And as we covered in the notes, Boyle didn't boil, so he keeps the temperature of the gas same. As the pressure on the gas increases, the volume or the space it takes up decreases. And the opposite is true, is the pressure decreases, the volume or the space the gas takes up increases.
Boyle's law states that in a closed system, pressure and volume are inversely proportional. What that means is that as pressure increases, volume will decrease and vice versa.
The only equipment you can need this episode includes a large syringe that you can get at a medical supply store or drugstore,
and water balloons, which we found to work well because of their small size. Although we're not dealing with anything hazardous in this episode, it's never a bad idea to wear some eye protection and a lab coat or apron. The first step in our experiment is to blow up our water balloon. Keep in mind how large it is, as it still has to fit inside the syringe. Once you have it to a good size, just tie it off, like so, and you're ready to go.
The next step in our experiment is take your small balloon in your large syringe and drop the balloon inside the syringe and place the plunger on the end. For our first test, place the plunger at the highest.
Now, right now, the pressure on the balloon is the same as the outside air pressure, so nothing's changed. He's going to increase the pressure on the gas by pushing down on the plunger of the syringe. When he does that, the gas inside the syringe, as the pressure increases, the volume or the space it takes up will decrease.
Point in the syringe and cover the bottom opening with your finger. Next, press the plunger down and watch as the balloon shrinks.
So 2 things happened here. One, he increased the pressure by pushing on it, and that decreased the volume of the actual space that the air inside the syringe took up. Because this air is under higher pressure, it's also pushing on the balloon harder, and you can see the evidence of the higher pressure because the volume of the balloon also decreased.
In size. Remove your finger from the bottom of the syringe to release the pressure. For the second test of our experiment, we're going to place the plunger at the lowest point it can be without touching the balloon. Once again, place your finger over the opening in the bottom of the syringe and pull the plunger upwards. Watch as the balloon.
By doing that, he's increasing the volume, which means he's decreasing the air pressure inside the syringe, and the air pressure inside the balloon is staying the same. So because there's less pressure on the outside and the same pressure on the inside, the balloon is expanding.
The balloon increases in size. To release the pressure, remove your finger from the opening in the syringe. Let's look at this experiment a little closer. Boyles gas law states that when a fixed amount or mass of an ideal gas is kept at a constant temperature and in a closed system, then its pressure and volume are inversely proportional. What this means is, when pressure increases, volume decreases, and as pressure decreases, volume increases. An ideal gas.
So they're going to apply the pressure by pushing on the top of this syringe.
Gas is a theoretical gas composed of a set of randomly moving, non-interacting particles. Under normal conditions, many gases such as oxygen, hydrogen, and some heavier gases like carbon dioxide will behave like an ideal gas. This means they follow the laws of ideal gases, such as Boyles Law. In our experiment, the balloon and syringe are filled with tons of gaseous air molecules. Placing your finger over the opening at the bottom of the syringe keeps the mass of air molecules constant and creates a closed system that will allow us to manipulate the pressure and volume. When we press the plunger down, we are increasing the pressure being placed on the air molecules inside the syringe by reducing its volume. As the pressure increases, the amount of force placed on our air molecules increases and they are forced closer and closer together, decreasing the volume of space that our gas takes up and shrinking the size of our balloon. When we remove our finger from the bottom of the syringe, we release the added pressure and our balloon grows back to its original volume. In the second portion of our experiment, we start with the plunger at the bottom of our syringe, almost touching the balloon. When the plunger is pulled upwards, we are reducing the pressure inside the syringe by increasing the volume of space the air inside takes up. This decrease in pressure and increase in volume pulls the air molecules further apart, increasing the amount of space the gas takes up, growing and expanding the size of our balloon. Removing your finger from the bottom of the syringe returns the pressure back to normal, reducing the volume and size of our balloon. When we compare the two variations of this experiment side by side, we can clearly see the inversely proportional relationship between the volume and pressure of an ideal gas. This relationship is known as Boyles Law.